So in this video, we're going to go back to the molecular orbital diagram for octahedral ML6 type complexes, and we're going to add something. And so far, we kind of got distracted, right? We got distracted down this whole path of electron counting. It was a very interesting ramification of the molecular orbital diagram, but we didn't include pi bonding interactions. We assume there's no pi bonding, which is true for a good number of ligands can only form sigma bonds, okay? But a good number can also form pi bonds. And so now we're going to take that into account. So just like we did, if you remember back in chapter 5, we did an MO diagram at the end of chapter 5, an MO diagram for carbon dioxide. We made salts based on p orbitals. And so we're gonna have to do the same type of thing here. The sets of px and py orbitals are those that can do pi bonding, right? Because that's the orientation of a p orbital that you need in order to get two lobes overlapping. Now, note this could be technically a d orbital, but most ligands don't have transition metals in them. There are some, but that's pretty rare. Okay, so we're talking about your classical ligands here that can do pi bonding. So we have px and py orbitals, and we're representing them as vectors, okay, on each of the points of the octahedron. And so, these vectors can represent occupied p orbitals, those that aren't involved in sigma bonding, of course. So these could be px and py orbitals on halide ligands. And so you can get some pi bonding, for example, in these chromium halide complexes that can happen. These are called pi donor ligands, okay? These are basically electron density from the ligand is going to the metal, and you're forming a pi bond that way. Or this could be unoccupied pi symmetry, atomic orbitals or molecular orbitals on ligands. So those could be empty, anti-bonding, for example, pi orbitals of, for example, carbon monoxide and cyanide. And really, you're going to need to figure out, in order to do this without me telling you the answer, you're going to have to calculate the molecular orbital diagram for these ligands. Now, for the purposes of this course, usually we won't do that, although some of the homework problems walk you through this, okay? Specifically for carbon monoxide, it's a great example where you can understand how this pi accepting nature, so these are pi accepting natures, how they receive ligands, how they receive electrons from the complex. So it's a metal binding, giving electron density into those unoccupied molecular orbitals. All right, and so it turns out you can account for all of this in a simple MO diagram, okay? So again, we have our same, we're jumping right to the answer here, but we know where this all comes from. This is your d orbitals, right? This is your s orbitals, this is your p orbitals. We know the symmetry of these different orbitals. We get that from the periodic table. And then we can calculate what the symmetry of the pi sulks would be, okay? Now, I didn't do that, but I trust that you could go through, if you wanted to, and figure out how these vectors transform in all the different symmetry operations for octahedral space, and then you'll get a reducible representation. You could use a projection operator to visualize those. You could get the symmetry. The symmetry ends up being T1G, T2G, T1U, and T2U for your pi sulks, and we already did the sigma sulks more in detail. We did A1G, EG, and T1U. And so then you start just making interactions. And so, really the main thing that changes here, these sort of interactions are similar to before. We had our sigma bonding interactions, and I'm showing these all three kind of lumped together. But really, these are three separate lines, right? We walked through this on the previous diagram. We had A1G, T1U, and EG. Those can all bond with the sigma salts. But before we had these T2Gs were non-bonding, but now they can be bonding with these pi sulks. So you get a bonding T2G and then an anti-bonding T2G. So this becomes actually an anti-bonding. We still have delta O from crystal field theory, that's still there. Depending upon the nature of the complex and where these pi salts are, right, this could go up and down, and that could kind of shift some of these energy levels. How do you predict that? That's hard, right? That you need some experimental evidence, or you need to actually do the explicit quantum mechanical calculations of the energies of these MO diagrams. All right, but basically, now you're going to have a non-bonding T1U, or maybe it's weakly bonding if it can interact with this T1U up here, but that's pretty high in energy. So that's why I put non-bonding or weakly bonding. And then you have these extra non-bonding pi orbitals. Those are ones left over from the salts, the T1G and the T2U. And so all this is to say, this is why different ligands are different in the spectrochemical series. It has to do with how pi bonding they are, how pi anti-bonding they are, and well, the energies of these, right? And so that's why the spectrochemical series is hard to intuit. You need to go through this MO diagram analysis, and for each ligand, you'd have to know something kind of about the energies of these and figure that all out. And so something like cyanide or CO, that's a pi accepting ligand, okay? And that's a strong field ligand. So that means that because it's a strong field ligand, it's gonna have a very large delta O, that's one thing. And because it's a pi accepting ligand, it means that electrons are going to come in and from the metal and fill those high-lying pi star antibonding orbitals on the ligand. So what I just want you to know is that, you know, the spectrochemical series is complicated to rationalize. It comes from the individual MO diagrams for all of the ligands and how the energies interact when you mix them with atomic orbitals of a metal.